Hi, this is going to be the first video for Chapter 5. We're going to give an introduction to double bonds as the functional group of alkenes. So double bonds are basically usually appear for sp2 hybridized carbons. sp2 hybridized carbons will have 3 sp2 hybridized orbital and 1 unhybridized p orbitals. So between two sp2 carbons, they would form a pi bond between the unhybridized p orbitals and with 3 other hybridized sigma bonds. Now, because there's a pi bond which is perpendicular to the plane of carbon-carbon bond, which will result into a perfect planar geometry of double bonds. So in any double bonds, there's always one pi bond, one sigma bond, and the geometry is always perfectly planar. In this case, you can see not only 2 carbons, but also 4 hydrogens are also on the exact same plane with a completely flat structure. And the bond angle here is about 120 degrees because each sp2 carbon would possess a perfect perfect triangle around each carbon. Now, one thing to keep in mind is double bond is completely unrotatable. So this flat structure will remain as the structure of the alkenes at any time. It doesn't rotate. And it's not hard to imagine double bond, which is a sigma bond plus a pi bond, is stronger than just a single sigma bond. The bond energy is significantly higher. The difference is the pi bond. And because of the pi bond, which is extra pair of electrons between 2 carbons, so that makes the carbon double bond particularly more reactive than the single bond. Now, usually when we look at any alkanes without double bond or with sigma bonds only, we say this is a saturated hydrocarbons, meaning all of the carbons are saturated with the maximum number of hydrogens. Whereas in the alkene, when there's a double bond between 2 carbons, now on each one of these carbons, they're going to have 1 less hydrogen on it compared to the correlated alkane structure. So between 2 carbons, there will be total 2 hydrogens missing compared to the alkanes. We call it unsaturated hydrocarbons. Unsaturated hydrocarbons refer to any hydrocarbon with double bonds or when you have pi bonds, which could be 1 double bond or more than 1 double bond, or sometimes could be even triple bonds. Now, in order to understand the unsaturated or the saturated degree of unsaturation, we can basically look at the structure or the formula of the pi bonds. So when you have a certain number of carbons in the hydrocarbons, let's say this number is going to be n. N is the number of carbons, and is also any integer numbers, can be 1 to any numbers, 2, 3, 4. The corresponding number of hydrogens is going to be 2n plus 2. So for example, if you have 1 carbon, when n equals to 1, the number of hydrogen will be 2 times 1 plus 2, which is going to be 4. And then when n equals to 2, the saturated hydrocarbon would have 2 times 2 plus 2 equals to 6 hydrogens. Now, when you have completely saturated the hydrocarbon, and that is going to be the molecular formula of it, CnH2n plus 2. Like what we said earlier, with any 1 pi bond or 1 double bond, you're missing 2 hydrogens. In other words, with every pi bond or ring, we're going to have 2 less hydrogens. Here we need to point out the similarity between the ring and the pi bond. A pi bond obviously is the second bond or the third bond in a triple bond. A ring which doesn't have any pi bonds could also result into missing 2 hydrogens. For example, with 5 carbon cyclopentane, there are only 10 hydrogens instead of 12 hydrogens. The ring doesn't follow the CM H2N plus 2 rule, it actually is going to be similar to a double bond structure. In other words, if you have a cyclic structure and a double bond at the same time, then you're going to miss in 4 hydrogens. The formula will be CN2M H2N minus 2. That's 4 hydrogens shorter than the regular saturated hydrocarbons with CnH2n plus 2. So we can use basically number of hydrogens here to measure the degree of unsaturation. Every 2 hydrogens missing from the saturated molecule, we say is 1 degree of unsaturation. Now we call this, when we say degree of unsaturation, we can also name it as double bond equivalence. So from the previous discussion, we already know that double bond equivalence can be a double bond or a ring. Now each double bond or each pi bond, let's put that way, count as 1 double bond equivalence, as well as each one of the ring structure. So for example, if you have structures, then you don't have to count hydrogens. You just look at the number of double bonds or the rings. So in this first example, you can see here, there's a 1 double bond, so we say this molecule possesses a 1 DBE. The second structure here, we also see 1 double bond. There's also 1 DBE. Notice that the double bond we're talking about are not only limited to carbon-carbon double bond, we're also talking about any double bonds, even with header atoms such as oxygen or nitrogens. They also count towards DBEs. In the third structure, you can see there's a ring as well as a double bond. So ring counts as 1 DBE, and double bond, the CN double bond, also counts as 1 DBE as well. Therefore, in this structure, there are a total of 2 DBEs. In the next structure to the very left, there's a ring and there are 3 double bonds. So 3 double bonds plus ring total 4 DBEs. In this structure, we can see there's only 1 triple bond, but this triple bonds, every triple bond has 2 pi bonds. So every triple bond counts as 2 DBEs without any other double bonds or rings. Next structure, this is a cyclopentane ring. This ring has no other double bonds, but the ring itself counts as 1 DBE. So this compound has 1 DBE. And the last structure here, there's 1 carbon-oxygen double bond, even with another hydroxy group which has no impact to DBEs. Without any other double bonds or rings, this compound has 1 DBE. This is when you have the structures, but what if you are not given structure but only given the formulas? How do you determine the DBEs? And here's the rule, and we're going to give examples to show you how to imply this rule. So when you are given a formula of the compound, you need to identify the number of carbons first. Let's say you have n carbon, and then we're going to find the number of hydrogens for saturated hydrocarbons with the corresponding carbon. Now, let's be clear here. The CnH2n plus 2 is not the molecular formula of the specific compound you're looking at. It just gives you a calculation of how many hydrogens you should based on or should starting of the calculation. If you have n carbons in the molecule, then the saturated hydrocarbon will be the number of hydrogens. The saturated version of the hydrocarbon would have 2n plus 2 hydrogens. And this number you can use as a reference to compare to. It is not your molecule. And then you should go to your actual molecule to find out how many effective hydrogens in the actual compound and compare that number of hydrogens with 2n plus 2 number of hydrogens to figure out the number of DBEs. The specific way of looking at this actual molecule is this. For each hydrogen, of course, you need to count as hydrogen. For each halogen, you should also count it as 1 hydrogen as well. For each nitrogen atom, you should minus 1 hydrogen. For each oxygen, you just ignore it. Now, once you complete counting the effective hydrogen, you should use the number of saturated hydrogen, 2n plus 2, minus what you just counted, and divide by 2. That's going to give you the number of DBEs in this molecule. And let's take a look at a few examples here. We're going to start by looking at the structure on the right hand side, since that's something we already looked at. The structure on top here, you can pause the video here, see if you can try this yourself first. Now we're going to from top left here and go to each structure first, and then go to the chemical formulas on the left. The first structure here, there's only one double bond. That means there's a 1 DBE. And then the next structure to the right, which has a triple bond. A triple bond is basically counted as 2 pi bonds. So this counts as 2 DBEs. Then this square-shaped molecule, there's a ring. Every one ring counts as 1 DBE, and there's no pi bonds, either double bond or triple bond. So this compound has 1 DBE. The structure in the center has a ring and 3 double bonds. So each double bond counts as 1, 3, and the 1 ring, which also counts as 1. So 3 bonds plus 1 ring equals 4 DBEs. The structure to the right, you can see there's a ring. The tail doesn't really count towards anything, but there's a ring and a double bond, so there are 2 DBEs. The structure down here, even though it looks like, but it's not a ring, but there are 3 double bonds, so there are 3 DBEs. Now let's take a look at these formulas, chemical formulas. Without structure, we won't be able to see exactly whether it has a double bond or ring or anything, but we can count the hydrogens. The first thing you're going to do is look at the number of carbons. For example, in formula A, there are 6 carbons. Then we have to, based on this number of carbons, to calculate the saturated version of this molecule would be 2 times 6 plus 2. Then that would be 14 hydrogens. And then the actual formula, the C6H14 is the saturated version, but the actual molecule is C6H10. So the saturated number of hydrogen minus 10 hydrogen divided by 2. So we can see the first molecule actually has 2 DBEs. Similarly, we can look at B, C9H14. The saturated version will be C9H 2 times 9 plus 2 equals to 20. So the saturated number of hydrogen is 20. The actual molecule has only 14. So 20 minus 14 divided by 2 equals to 6 divided by 2 equals to 3 DBEs. C7H16, sorry. C7H 2 times 7 plus 2 equals to 16. So the saturated version of this molecule should have 16 hydrogens, and this molecule does have 16 hydrogens, and that means this molecule is saturated, or in other words, it has no DBE, 0 DBE. In D, there are 5 carbons. If it's a saturated version, the hydrogen number will be 12. 2 times 5 plus 2. Now this molecule has 11 hydrogen and also a nitrogen. So the effective number of hydrogen of this actual molecule is C5H11 minus 1. When you have a nitrogen, the number of hydrogens minus 1, so it will be H10. So the difference between the saturated version and actual molecule number of hydrogen is 12 minus 10 divided by 2, which equals to 1 DBE for D. Now let's look at the E, C12H21NO. First of all, you're only going to solve based on the number of carbons, figure out the saturated version of this molecule would be 24 plus 2 will be 26. The effective number of hydrogen here is only 21 with the nitrogen and with the oxygen. So the actual molecule is C12. The effective number of hydrogen is 21 because of the nitrogen, or minus 1. And oxygen does not affect anything. You don't have to count it. So it's going to be H20. The difference is 26 minus 20, and don't forget divide by 2, you're going to get 3 DBE. And that's for E. For F, there's C8H8OCl2. The number of carbon is 8, so the saturated version of this molecule will be C8H2 times 8 plus 2 equals to 18. So you should have 18 hydrogens. But this molecule only has 8 with 1 oxygen and 2 chlorines. The oxygen does not affect the number of hydrogen, but the chlorine counts as hydrogen. Should plus 1 hydrogen for each. So the actual number of hydrogen in this molecule is actually H8 plus 2. That will be 10. Now the difference between these two numbers, between the number of hydrogen is 18 minus 10 divided by 2, which is going to be 4 dBEs.